All right, welcome back, everyone. We're going through the Rust programming language book, and we are on to enums and pattern matching. We'll just jump right in, shall we? So, in this chapter, we'll look at enumerations, also called enums. And some people are like, should it be enums because it's enumeration? I don't know. I say enums. And then enumerations. Hmm, can't expect consistency, I guess. But anyway, enums allow you to define a type by enumerating its possible variants. So it's like a canonical set of values. It's the thing we're saying these are all of the things that this can be, and that anything else is considered an undefined thing. First, we'll define and use an enum to show how an enum can encode meaning along with data. That seems pretty good. So next, we'll explore a particularly useful enum called option, which expresses that a value can either be something or nothing. Definitely, options are one of the more useful enums that are just built into Rust, and as it's suggesting here, it either contains something or nothing. And like in a lot of programming languages, you often have to deal with some kind of like, is there actually a value or is it something like a none? And so handling that, what do you do? Rust provides pretty like built-in way to deal with that. So then we'll look at how pattern matching in the match expression makes it easy to run different code for different values of an enumeration. Finally, we'll cover the if-let construct, which is another convenient and concise idiom available to handle enums in your code. Yeah, it's just a way of like quickly checking, is there something, and if there is, assigning a variable name to it, and otherwise continuing on to the next block. Great, so let's talk about defining enums, where structs give you a way of grouping together related fields and data, like rectangle with its width and height. Enums give you a way of saying a value is one of a possible set of values. For example, we may want to say that rectangle is one of the set of possible shapes that includes circle and triangle. So one of the things that gets quite tricky at an implementation level that I think about sometimes is in mathematics, that we have different kinds of mathematical sets, and some of them are actually very difficult to say what is the set of possible values. And so I think this is actually one of the things where, on the face value of it, I don't think enums in Rust or other programming languages are really, maybe I shouldn't say all the other ones, but it's harder to start saying, oh, is this a member of something? You could start saying, here is like a function that checks if something's a member of a set, and then doing some kind of logic to see if it holds certain properties that you could imagine writing in like set builder's notation. But when you have to enumerate all of the answers, we're really talking about finite sets, and sets that we can definitively answer in a usually short amount of time, but in principle some amount of finite time, whether it is actually a member of a set or not. And obviously, undecidable things are just off the table. So, for example, we may want to say blibbity blatty. All right, we did that. So, to do this, Rust allows us to encode these possibilities into an enum. Let's look at a situation where we might want to express code in code and see why enums are useful, more appropriate than structs in some cases. Say we need to work with IP addresses, for example. Currently, two major standards are used for IP addresses, version 4 and version 6. Forget about all the other versions of like what happened to 1, 2, and 3 and what happened to 5, because these are the only possibilities for an IP address that allow our program to come across, that it should be allowed to come across. We can enumerate all possible variants, which is where enumeration gets its name. Totally. All right. So any IP address can either be a version 4 or a version 6, but not both at the same time. They're mutually exclusive categories. Okay, great. So that property of IP addresses makes the enum, I just did enum, look at me go, data structure appropriate because an enum value can only be one of its variants at a time. Both version 4 and version 6 addresses are still fundamentally IP addresses, so they should be treated as the same type when the code is handling situations that apply to any kind of IP address. We can express this concept in code by defining an AP adder kind enumeration and listing the possible kinds of IP addresses that there can be. We'll call them v4 and v6. These are the variants of the enum, right? So I suppose we should we'll leave the print hello world for a moment, and we'll just define our enum and go along with what they're doing here. So we've got IP adder kind, and inside we're saying there's a thing called v4 and v6. Thank you, auto format, for adding a comma. IP adder is now a custom data type that we can use elsewhere in our code. Totally. Otherwise, if you couldn't, I don't know what the point of just declaring this thing would be, other than, you got to use it somewhere. So we can create instances of each of the two variances of IP adder like this. Okay, so we can define and assign to Rust variables something like v4 and v6. Look at that. Note that the variants of the enum are namespaced under this identifier, and we use a double colon to separate the two. This is useful because we now both values IP adder kind 4 and IP adder kind 6 are the same type according to Rust's type system. We can then, for instance, define a function that takes any IP adder kind. So function definition route takes an IP kind, you pass in the kind of IP, and we can call this function with either variant. All right, so let's define this function, IP kind, and we're going to say we defined this as a type. This is one of the things that we can do here is actually add types to not the Rust core, obviously, but to our Rust program. So then we can, I don't know, this function in their example doesn't do anything, so I guess we'll just leave that. And we can call this function, right? So let's do it. Let's call route for route. I mean, their example, they're passing directly in, but these are really the same. Are they not? Let's just do a cargo check. Should be run. I guess I ran instead of checked. But anyway, whichever way, complaining that we didn't use this variable, that's fine. For this example, there is a way to actually turn off these warnings, but I kind of like them. Generated one warning, sure. Maybe that won't be true if we start building something really big and then there's a whole ton of them, but I think it's good to just be persistent in reevaluating whether something should be reused within the code or not until explicitly turned off. Okay, so that doesn't do anything of interest yet, but that's a thing we can do. Using enums has even more advantages. Thinking about our IP address type. At the moment, we don't have a way to store the actual IP address data. We only know what kind it is. Given that you just learned about structs in Chapter 5, you might be tempted to tackle this problem with structs as listed below. So let's go cargo example 1. Got to actually say that I want a new project. Example 1. Right, so we could do something like this, our IP adder kind. So they're not saying replace the whole thing with struct, but this particular aspect of going I've got a type and then really there's data related to that. IP adder kind, and then we define this struct, which is the address itself. So they were kind of careful about their naming, where they say this is a kind of thing, it's not the thing itself. And then the struct is going to be the definition of what a thing itself, an address in this case, is structured by. So then they might say, well, an address is a string, and a kind is an IP adder kind. And then we might, let's put this inside of main, we might say let home, a home address, equal IP adder. And then we'd say that the kind of address is IP adder version 4, and the address itself, let's see if my LSP rename is working. Yeah, it is great. Excellent. So then we'd say our address, and then we say our home address is 127.0.1. 1. Right, that's our home address. Semicolon at the end there. And then we might say there's a loopback address. Adder. Here we might say that the kind is IP adder v6, and the address is string from 1. Great, so that runs. Storing the data and the IP adder variant of an IP address using struct. So really this becomes a matter of saying we want to say that there's like an IP address, and that we're going to declare this kind, and then we actually have to pass in some kind of representation. In this case, we chose string in the example for our IP address. Here, we've defined a struct IP adder that has 2 fields, a kind field that is sort of the type IP adder kind, the enum we defined previously, and an address field of type string. We have only 2 instances of this struct. The first is home, and that has a value of IP adder version 4, and it's as its kind, with associated address data of 127.0.0.1. The second instance is loopback. It has the other variant of IP adder kind as its kind value, v6, and has the address : 1 associated with it. We've used a struct to bundle the kind and address together, so now the variant is associated with the value. I agree. I mean, you don't actually have to add this kind of stuff, but it becomes especially handy if you're dealing with a lot of addresses, a lot of complexity, and you want some structured way for your brain to help you deal with it. What's kind of minimally required for the computer is not the same as what we humans tend to need in practice to keep track of things. So this is a pretty reasonable way to bundle things. But I have a feeling, like the way they phrased things, that they're eventually going to say there's another way to do this. And here we go. However, representing the same concept using just an enum is more concise. Rather than an enum inside a struct, we can put data directly into each enum variant. Great. String inside of v4, v6. I think or hope that there's going to be some kind of validation thing that they talk about. Otherwise, how do you know that it's really one of those things? But we'll see what we get to. This new definition of the IP adder enum says that both v4 and v6 variants will have associated string value. So create our... Oh, I created a Rust project inside of a Rust project. I'll fix that later. Now I'm back at home. My path, that's the issue. Okay, I'll just make another project here. So we'll go cargo new, call this example 2. And let's see. Let's define this enum for adder again, getting some practice typing it out. And we've got v4 is one of the variants, and it's going to have some kind of specific value string. And we'll do the same for v6. Great. And then we can say let home IP adder v4. Interesting that the default is to pass in a unit type. Okay, so from string, and then we'll pass in our 127.0.0.1. That's our home address. And then we can say for our loopback address, it's an IP adder. From colon, colon 1, and then with the semicolon. So I think that this is sufficient. Let's just run it. Must have put in a mistake somewhere. Let's see, IP v4 string, v6 string. Yeah, let home IP adder v4 string from blibbity blabbity string, loop back IP adder v6 string. You know what I should actually do is read the error. Or they're just warnings, I see. Still, let's read what they are. Okay, so there's some complaints that we didn't use the home variable or the loopback variable. That's fine. V0, it's never read. So I never actually used the value somewhere. That's neat. Consider changing the fields to be of unit type to suppress this warning while preserving the field numbering. Could. Or remove the field. Oh, I see. No, we're not going to do that because we're just following the example as it's given to learn from it. So that's fine. My only kind of complaint so far about the example, it's not a complaint really, but a thing I would say should be added is some kind of validation. Otherwise, can't this just be whatever kind of random string, right? So some additional validation, I think, is warranted there. And there's where, I don't know, what would I do? Write an implementation function that like says create one of these IP adders, but like it gets validated as you make it, perhaps, maybe something like that. Or if worst comes to worst, like I shouldn't say worst comes to worst, but you could use potentially like a factory pattern, get a function that builds it for you, validates the inputs, and then builds the enum. But I think I like the idea of using an impl here more. Maybe I'd have to think about that more. So let's get on to the next piece here. We attach data to each variant of the enum directly, so there is no need for an extra struct. Here, it's also easier to see another detail of how enums work. The name of each enum variant that we define also becomes a function that constructs an instance of the enum. Yeah, I noticed that. It's pretty cool. That is, IP adder version 4 is a function that calls a string argument and returns an instance of the IP adder type. So I wonder if we're doing validation, if we can kind of override that function a little bit. That'd be interesting. We automatically get this constructor function defined as a result of defining the enum. I think that's pretty great. There's another advantage to using an enum rather than a struct. Each variant can have different types and amounts of associated data. Well, that's true. Version 4 IP addresses will always have 4 numeric components that will have values between 0 and 255. Oh, I see. Yeah, it's going to have different shape properties. That's interesting. Version 4 numeric values, 0 to 25. If we want to store version 4 addresses as 4U8 values, but still express V6 addresses as one string value, we wouldn't be able to do that with a struct, at least not in the straightforward way that they're talking about. So enums handle this case with ease. So I like that a bit. Instead of like string U8, U8, and actually, while that doesn't completely address the validation concerns in the broad strokes, partly because you'd still need some way of validating the V6 variant, it at least has an interesting. Oh, I'm casting from a string here. There's some cleanup here. So that actually simplifies creating them when they're V4 a bit, and that gives you some type safety stuff about, you know, what happens if I accidentally pass in a float. It should give an error. Yeah, mismatched type. I can see it already. Cargo check, error, expected U8, found float. Great. And that might be one of the things to really think about with using Rust is how do you make the type system work for you, so that things just happen naturally by definition, by declaration, instead of writing lots of additional control flow logic of if this is true, then that's blah, 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 blibbity blabbity, you know what I mean. So we've shown several different ways to define data structures to store version 4 and version 6 IP addresses. However, as it turns out, wanting to store IP addresses and encode which kind they are is so common that the standard library has a definition we can use. Let's look at how the standard library defines IP adder. It has the exact enum and variants that we've defined and used, but it embeds the address data inside the variants in the form of two different structs, which are defined differently in each variant. So this is also good. We're expanding where before we had talked about, we could maybe put this sequence of U8s or a string, but like, can you start to define, an enum whose variants are of some values that are structs of some type of struct? I assume you can also put like enums inside of enums in their definition and so forth. So I think you should be able to build out whatever structures you want there. Okay, so let's struct IP v4 adder. So they've written snip here, basically meaning that they're not defining it up front for us. I am curious, take a little quick peek at their IP adder. So they have these 4 and 6. I'm curious how they're actually defined though. It's private fields, makes sense. They already have some variants like localhost. You could assert like an adder here. Is it equal to new from 127.0.0.1? Sure, that's cool. Unspecified broadcast. Okay, I think we'd have to dig more into the source. IPv, the public struct, makes sense, it's public. Diagnostic term, or diagnostic item, don't know what that is. Rust diagnostic item. There's some things I got to learn here, and deriving some things like cloning so you can make copies of it, and defining some order relation on the set of addresses so you can sort them or whatever. I think this will take more time than I wanted it to, so we'll just say that, okay, fine, there's addresses, and we might look at that again sometime. But this code's not really worth typing out if that's all there is to it for this example. This code illustrates that you can put any kind of data inside of an enum variant, strings, numeric types, or structs, for example. You can even include enums. There's the answer to my question. Can you put enums inside of enums? Yes, you can. Also, standard library types are often not so much more complicated than what you might come up with yourself. Okay. Note that even though the standard library contains a definition of IP adder, we can still create and use our own definition without conflict because we haven't brought the standard library's definition into our scope, so there's no contradiction in the names. We'll talk more about bringing types into scope in Chapter 7. Great. Let's look at another example of an enum in listing 6-2. This one has a wide variety of types embedded in its invariants. Let's take a look. We've got enum message. One variant is called quit. Another is called move. That looks kind of like a struct to me. Write string and change color, which looks like a named tuple or whatever it's called. Okay. And a complaint that it's never used, but that's okay. A message enum that has variants, each storing different amounts and types of values. Great, so the enum has 4 variants with different types. Quit has no associated data with it at all. Move has fields, like a struct does. Write includes a single string. And change color includes 3 I32 values. Now, what's kind of interesting to me about this move, okay, it's going to be a type message, but it looks like a struct, but I didn't have to define a move struct. That is fascinating. Are they going to show initializing it? Defining an enum, the following structs could hold the same data preceding the enum. Let's get into this. We'll just follow their example because I have a feeling like they're going to take us there anyway. Okay. The enum has 4 variants. Right, we just read that. Defining an enum with a variance as listed is similar to defining different kinds of struct definitions, except the enum doesn't use the struct keyword, and all the variants are grouped together under the message type. The following structs could hold the same data that the preceding enum variants hold. So you could have a unit struct. It doesn't take anything. It just is basically a named type in the system. You could have this move message struct. Move message has a couple of I32s named X and Y inside of them. Struct write message takes a string, so it's a tuple struct. Struct change color message with 3 I32s is a tuple struct. But if we used the different structs, each of which has its own type, we couldn't as easily define a function to take any of these kinds of messages as we could with the message enum defined in listing 6-2 with a single type. There is one more similarity between enums and structs. Just as we're able to define the methods on structs using impl, we're also able to define methods on enums. Here's a method named call that we could define on our message enum. So I'm just thinking here, before we get into that code example, I'm just thinking, like, why would we want to then use structs versus enums if you can basically put almost any kind of data, as well as having impls and stuff? I think there's like a design choice to think through of what are the trade-offs between enums and structs. Not that they're mutually exclusive on all of your code, all or nothing, but just, when to use one in a particular case or not. Anyway, okay, so we can write out impls. Here's an implementation for message, and we'll call fun call. Takes in a reference, an immutable reference to self. Method body will be defined here. Yeah, it just looks and feels like a function, no problem. And then we'll say inside of our main message, write, and then we could say string from hello. Sure. And then we could even call this function m.call. Right, it's also complaining that I'm not using that type again, which is, it's okay. Yeah, so we would want to probably access some of the data that's inside of the variant when we do this, but for now, I guess we're just saying we can define a function, which is good to know. The body of the function would use self to get the value that we called the method on. In this example, we've created a variable m that has the value message write string from hello, and that is what self will be in the body of the call method when m.call runs. Let's look at another enum in the standard library that is very common and useful, the option type. So the option type, this section explores a case study of option, which is another enum defined by the standard library. The option type encodes the very common scenario in which a value could be something or it could be nothing. And I wouldn't say that this is a Rust thing, like this is a very common issue. The option type is not super common among programming languages, and some programming languages inspired by Rust have had libraries developed. I think, what is it called, like the results library or something like that for Python, you can have like an option type. I'm getting option and result mixed up. There are actually libraries in Python that try to emulate both the result type and the option type. But anyway, suffice to say, this is a thing, and it's actually a pretty common thing to say, well, I've pulled in something that might contain data, but I don't know what it actually contains. So, for example, you request the first item in a non-empty list, you would get a value. If you request the first item in an empty list, you would get nothing. Expressing this concept in terms of the type system means that the compiler can check whether you've handled all the cases you should be handling. I love that about compiler checks. This functionality can prevent bugs that are extremely common in other programming languages. Sure. Programming language design is often thought of in terms of which features you include, but the features you exclude are important too. I feel like this is a wonderful thing. It's one of those things that I would bucket in great advice. I wish people could follow it more, but you know, I don't know. People sometimes can't refrain from really adding more stuff than that is actually needed. Anyway, so Rust doesn't have the null feature that many languages have. Null is a value. That means there is no value there. In languages with null, variables can always be one of two states, null or not null. True. In this 2009 presentation, Null references the billion-dollar mistake by Tony Hoare. The inventor of the null type had this to say. I don't know if it's Hoare or Hoare. Tony Haw or Hoare. Door, core, I don't know. Anyway, the inventor of null had this to say. I call it my billion-dollar mistake. At that time, I was designing the first comprehensive type system for references in an object-oriented language. My goal was to ensure that all use of references should be absolutely safe, with checking performed automatically by the compiler. But I couldn't resist the temptation to put in a null reference, simply because it was so easy to implement. This has led to innumerable errors, vulnerabilities, and system crashes, which have probably caused $1 billion of pain damage in the last 40 years. What a rough thing, eh? Clearly, type systems like this are immensely useful, but sometimes you can put in too much. When do you really need a null type? A null reference, I should say. I'm not even sure I know enough about type theory to say, are there certain things you can only do with a null, but yeah, so very often in practice, I don't think you need one, but it is navigable having one. You just have to be more careful. So the problem with null values is that if you try to use a null value as a non-null value, you'll get some kind of error. Generously, or worse, you get some kind of undefined behavior. Because this null is not null property, because this null or not null property is pervasive, it's extremely easy to make this kind of error. Yeah, like if you knew you were doing something that can definitely go wrong, but you don't have to do it all that many times, you can kind of just set aside the time, attention, and energy to make sure that you do the thing right. But often when you're busy trying to do dozens of things at once, so at least somewhat concurrently, then yeah, like this just becomes some little thing that's an afterthought. You can get it wrong without really even noticing until it's too late. So, however, the concept that null is trying to express is still a useful one. A null is a value that is currently invalid or absent for some reason. The problem isn't really with the concept, but with the particular implementation. As such, Rust does not have nulls, but it does have an enum that can encode the concept of a value being present or absent. Yeah, that's nice. This enum is option of whatever type and is defined by the standard library as follows. Enum, option type, none, some of that type. The option T enum is so useful that it's even included in the prelude of Rust. You don't even need to bring it into scope explicitly. Its variants are also included in the prelude. You can use some and none directly without the option prefix. The option type enum is still just a regular enum, and the sum of T and the none are still variants of the type option of T. The T syntax there, the less than T greater than syntax, is a feature of Rust we haven't talked about yet. It's a generic type parameter, and we'll cover generics in more detail in Chapter 10. For now, all you need to know is that T means that some variant of the option enum can hold one piece of data of any type, and that each concrete type that gets used in place of T makes the overall option T type a different type. So it's a class of types, not just a specific type. When you want to think about it conceptually outside of the compile time, here are some examples of using option values to hold number types and char types. Sure. Actually, we don't even need, it's just part of the prelude. There's nothing to include. So let's just go let some number be bound to the value of sum 5, and let some char be bound to the value of sum thing there, and then let absent number be bound to the value of option I32 equal to, oh, you need a colon there. So the type of sum number is option I32. The type of sum char is option char, which is a different type. Rust can infer these types because we've specified a value inside of the sum variant. For absent number, Rust requires us to annotate the overall option type. The compiler can't infer the type that the corresponding sum variant will hold only by looking at a none value. Here we tell Rust that we mean for absent number to be of type option I32. Now, when we have a sum value, we know that a value is present, and the value is held within the sum. When we have a none value, in some sense, it means that the same thing as a null value. We don't have a valid value, so why is having an option t any better than having a null value? Right. In short, because option t and t, where t can be of any type, are different types. The compiler won't let us use an option t value as if it were definitely a valid value. For example, this code won't compile because it's trying to add an I8 type, an integer signed type of 8 bits to an option. So if I try that, let's try that. I might say let x I8 be bound to the value of 5, which is okay. It's an undefined value. Then I say let y option I30, or sorry, I'm so used to I32, I just want to say I32, but anyway, okay, so sum of 5, that's also fine. All of that's good so far. We can define something as a sum type or as a literal I8 type, but an option type, I should say. But if I go sum and I try to take the sum of the two, then I'm requiring using the values of two different types that are not defined to have some kind of addition. Cannot add an option I8 to an I8. And that's because think about if the y value is actually a none type, then you have 5 plus none, which doesn't actually mean anything. It's undefined. And so Rust's way of dealing with optionality as a type means that it's explicit and checkable by the compiler ahead of time before you even run something to go, this can't actually be a thing. You're not comparing apples to apples yet. Okay, so if we were to run this code, we would get an error. Sure, let's try to run it. Cargo run, could not compile it because of obvious reason. They say it's intense. I don't know if it's intense. It's just not valid. That's fine. In effect, this error message means that Rust doesn't understand how to add an I8 and an option I8 because they're different types. When we have a value of a type like I8 in Rust, the compiler will ensure that we either always have it will ensure that we always have a valid value. We can proceed confidently without having to check for null before using that value. Only when we have an option I8 or whatever type of value we're working with do we have to worry about possibly not having a value, and the compiler will make sure that we handle that case before using the value. So in other words, if you have to convert an option type to a type before you can perform type operations with it, often you have to. Generally, this helps catch one of the most common issues with null, assuming that something isn't null when it actually is. Right, that would be the problem that we pointed out here. Eliminating the risk of incorrectly assuming a non-null value helps you be more confident in your code. I mean, I think so. I mean, of course, the subjectivity of that matters. You know, if you talk to somebody who doesn't write in Rust and they deal all the time with this issue of null, not null, they may already just have lots of good habits for dealing with that and being correct most of the time, or at least often enough that it's not a priority for them to like switch languages just for that. I think you can get used to dealing with it. But nonetheless, yeah, like it also provides some automated quality checks, which in some circumstances I think is quite beneficial. In order to have a value that can possibly be null, you must explicitly opt in by making the type of that value option type. Then, when you have to use that value, you are required to handle the case when the value is null, covering all of the cases. Something that you can learn to do by habit and convention, but this makes it a technological constraint that you can't do anything otherwise. Everywhere that a value has a type that isn't an option t, you can safely assume that the value isn't null. This was a deliberate design decision for Rust to limit null's pervasiveness and increase the safety of Rust code. So how do you get the type value out of a sum variant when you have a value of option t, so that you can use the value? The option t enum has a large number of methods that are useful in a variety of situations, which you can check them out in the documentation. I think we probably won't go through them all. We're not going to go through them all at all in this video, but yeah, there's like a whole bunch of different things you can do depending on the situation of unwrap, unwrap, or else unwrap, or default, etc., etc. So that's a whole can of worms of what can you do with an option type. That's good to know. But that the basic idea is very simple. Either something has a value or it doesn't have a value, and you should handle it. Becoming familiar with the methods of option t will be extremely useful in your journey with Rust. Can totally see why. Okay, so in general, in order to use the option t value, you want to have code that will handle each variant. You want some code that will run only when you have a some t value, and this code is always allowed to use the inner t type. You want some other code to run only if you have a none value, and that code doesn't have a t value available. The match expression is a control flow construct that does just this when used with enums. It will run different code depending on which variant of the enum it has, and that code can be used, can use the data inside the matching value. So you can have branching that is going to pattern match against what variant of the option enum, and then do different things, which I think is great. So that's enums at a first look. Of course, you can combine them with other things to get further and further refined functionality and definitions, and even when you look at the type system, dealing with some amount of validation of the structure of things. Hopefully that's useful, and I will catch you in the next video. Take care.